Hello, Physics 20s. I'd like to go through the introduction to simple harmonic motion. It's chapter 7, and today I want to talk about pendulums. So the first thing we need to understand in chapter 7 is a principle called simple harmonic motion. It's any situation where these two criteria are observed. If you have any object that repeats its motion over and over again, but it has to be in a fixed pattern that can be measured. And that, when I say measured, meaning the period, okay? So it needs to be a pattern that repeats, or something that repeats itself over and over. And the extension here is hopefully easy to get. In the past, we've talked about circular motion. So if an object goes in a circle, then the period is the time for one rotation. Okay, if we think of it that way. Okay, that's kind of ugly. So, but yeah, one rotation is the period, but now we're going to expand that just a little bit to consider objects that aren't necessarily moving in a circle, but they're just moving, but they're moving in a pattern that repeats itself. Okay, so that's the first criteria: is it needs to have a pattern and it needs to have a measurable period. The second one, though, is it needs to have a restoring force, FR, okay, that's causing the object to move back to its equilibrium point, okay, wherever it was at rest. The restoring force is directly related to the amount of displacement. Okay, so that's like Hooke's law. If you displace a mass on a spring farther from its equilibrium point, then the restoring force will be greater. It's directly proportional. So the two main examples we're going to look at are a mass on a spring. Okay, so if this mass right here, if it's oscillating up and down, like you pull it down, it'll go up and down with a specific period, and we're going to study that shortly. The other classic one, of course, is a pendulum, which we're going to get to today. Pendulum is just a mass that's tied to a string. Sometimes I call this part up here the pivot, but it's just where it'll hinge, and then the pendulum goes back and forth. So the period for a pendulum, and you'll see that in the notes shortly, is how long it takes to go all the way over and back. Okay, that's one complete movement, or one complete oscillation is a term we're going to use, right? And you've seen that. Another really cool one is that these periods can get really, really complex. And we see that in nature all over the place. There's thousands and thousands of examples. A hummingbird flapping its wings is a classic one. And actually, hummingbirds and insects, some insects have the same pattern in their, well, it's a very similar pattern in the complexity of their wing beat. And actually, I wanted to show you, oh, sorry, not that. Let's show you this right here. So here is a wing beat in here. Let me just, I think I turned the volume down here. Yes. So if you can see this, the oh, it looks like oh, there we go. Okay. So when a bee beats its wings are actually not big enough to cause it to fly. Like its wings are anatomically too small. So what the bee does is it oh, oops, just a minute here. I think I got the wrong one. Sorry about that. I wanted to show you how a bee wing actually or how a bee actually flies. So here, let's just pull this back up so you can see this. So the point is that the bee's wing actually, it knifes upwards, and then it goes flat and then pushes down. And then on the upswing, it knifes and then it goes flat and pushes down. And that's exactly what a hummingbird does. The hummingbird does the same thing, and it's a really cool adaptation to enable it to have smaller wings that can do the same job as a bird with bigger wings. But the point is that there's a very kind of complex movement of the wing, but it repeats itself. And hummingbirds and bees and all these other flying animals have they can do this pattern hundreds of times a second. Okay, so like I think a bee wing beat is about 200 hertz or 200 times um, a second. Okay, so I mean you can count 1,000. Okay, and it repeats itself 200 times. So it's very impressive, but it follows what we call simple harmonic motion. The terms that we will study are, a lot of them are you're familiar with already, but I'm just going to hit on three of them. The first one is amplitude. You'll see amplitude as represented as an A. It's going to come up in some of the formulas, mostly with masses on springs, but we define that as the maximum displacement from the equilibrium position. Okay. Sometimes I like to think of it as a special X. Okay, and I'll show you that when we get to masses on springs, because X is the displacement from equilibrium. That's what it is for a mass on a spring, or just a spring in general, and we're going to add a mass to it. But A is a special X, it's the maximum X. So frequency now, we're just expanding it a little bit because we're going to go beyond objects going in a circle, okay? So frequency now is like a specific pattern that repeats itself so many times per second. And we call those oscillations per second. Still measured in hertz though, so that's nothing new. Hertz is cycles per second. And the period, of course, is the same as we've studied before. It's just that now it's the time to complete a full oscillation instead of a circle. So these guys are reciprocal in their relationships. F is equal to 1 over T, or we could say that T equals 1 over F, and your guys are going to do that right away. In terms of waves, the period is the time it takes for one wave to repeat itself, okay? So we have a total wave, a crest and a trough. How long does that take for the crest and the trough to form? That's the period. And then we can also find the frequency of that wave. And we are going to get into waves coming up. So this video is just going to focus on pendulums. And the first thing we need to know about a pendulum is how do we calculate the restoring force on a pendulum? So you can see here in this picture, if we pull a pendulum to the right, there's going to be a restoring force, which is really going to be a component of the tension in the pendulum that's trying to pull the pendulum back to equilibrium. So if you look here at let's just look at part B here for a second. If we look at the if we look at a free body diagram right here, the force of gravity would be down and the tension in the cable would be up. And right there, those forces would be balanced. And so there wouldn't be a net force, there wouldn't be any restoring force at equilibrium, okay? This is what we're going to start calling our state of rest. It's a term I'm sure you've heard of, equilibrium, okay? So, but when you pull it to the side, like we did up here, now what's different, I mean, gravity didn't change. Gravity is still down, but now tension is this way, okay? That tension is that way. Now, there's two ways you can analyze the restoring force, because the tension isn't the restoring force, because really the restoring force, if we look at this, the restoring force is it wants to bring the mass back to where it was, or if in a sense it wants to bring it back to this specific point, okay? So how do we account for that restoring force? Well, let's just look at it in terms of the free body diagram for this one. The tension would be matched by the component of gravity that is perpendicular to the curvature of the arc. Okay, so you can see the curvature. If we just extended that, a 90-degree angle to that curvature would highlight the force of gravity perpendicular. Okay, there it is right there, the force of gravity perpendicular. Now, tension and the force of gravity perpendicular would equal each other, but there would be a 90-degree component of that we would technically call the force of gravity parallel, or the restoring force, FR. There it is. Okay, so that force, that component of the force of gravity, is working parallel to the curvature of the arc, the curvature of the movement of the pendulum, and it's trying to bring it back to its equilibrium position. So what's really nice about pendulums, it's the same with inclined planes, if you remember that trick. the angle that you displace your pendulum is also the same as the angle within the free body diagram, within these force of gravity components. So if you know the angle you displace it, it's the same angle there, and you can simply do the sine of theta multiplied by the force of gravity, okay? Because we're going to take the sine of that angle to give us the opposite value, which is going to be the force of gravity parallel. Now, some other students figured this out a while back, and I'll just maybe clear some of that off, because if you look at the whole thing again from our original analysis, you could say that the force of tension now it has to have a horizontal component and a vertical component. Okay, just the force of tension. And what's really cool is the vertical component of tension has to match gravity. Okay, so this force here and that force have to be the same still. Okay, so that's why there's more tension, because now we have to have it on a horizontal level. The tension actually is going to go up, but the vertical component has to stay the same. And if you use this angle and you make the force of gravity here equal to this would be the force of tension vertical, I guess, okay, in the y direction, and then the force of tension in the x direction, this is going to be exactly the same as this. This and this are exactly the same. That's really cool. So it depends on, and look, you have the same angle up here as you would have had in here. It's kind of like the triangle just got rotated, if you can kind of spatially see what I just did. Anyway, it doesn't matter how you analyze it. Either the first way, which is probably the easiest, or the second, you will both get the same restoring force on the pendulum. And yeah, it's proportional to how far away you displace it from equilibrium. But there are some limits with pendulums in this regard, and I highlighted that right here. So sorry, this is the formula. The restoring force is equal to the force of gravity, whatever the force of gravity is on the bob, times the sine of theta. And if you really had to analyze it further, which most times you won't need to, the restoring force is actually going to equal the force of gravity parallel on the mass if we do that free body diagram. Okay, so calculating the restoring force isn't too bad. The math's pretty straightforward. There are some limits, though, that are worth mentioning. If you displace any pendulum, by the way, any pendulum, if you displace it past 20 degrees, then the restoring force it's not linear. Okay, so it's really only good to about somewhere in the 15-degree range. Okay, so in there. Okay, but you get past 15 degrees, and then the restoring force doesn't follow a straight line like you would expect it to. So pendulums only follow kind of the laws of simple harmonic motion if you displace them less than 15 degrees. Okay, and potentially another video I'll show you how that works. But you'll see that in the questions. Okay, so the period for a pendulum. This is where it gets cool. So actually, I'm gonna back out of this quick, and I'm just gonna show you this this kind of summary of pendulum. So we'll just kind of walk through this a little bit here. So anyway, what's a pendulum? It's basically just a bob on a here. I'm gonna move this up here. A bob on a string, and it is very predictable in its movement, and it's no surprise that as soon as the scientific community, pre-1800s, I'm not sure exactly when this kind of kicked in, but as soon as they realized the consistency of a pendulum, it led immediately to the invention of clocks and pendulum clocks. Okay, because it was very reliable as long as you could do. There were some tricks to keep the pendulum swinging, but it quickly became the standard method for keeping track of time. You can also use it to measure the acceleration due to gravity, which you'll see shortly. And here's the cool one. It can prove that the Earth is spinning. So that you're like, what? How can a pendulum show that the Earth is spinning? Well, a man named Foucault. Actually, this is just showing the history here. A bunch of wrong ideas. People thought the Earth was flat. Yay. Anyway, and even Isaac Newton actually was looked for ways to prove that the Earth was spinning. They were limited a lot by the way their testing methods. You can see one here. They dropped a rock down a mine shaft. Can you tell that the rock is slightly moving to one side if the Earth was spinning? Really hard to tell. Or what about shooting a cannon really far? In the north-south direction to see if, as the Earth rotates, it kind of veers off of a straight line. Hard to tell. So Jean Foucault became famous for making pendulums, and the big pendulums that you can see in university science centers and other museums, they're called Foucault pendulums, named after him. So he realized that, and messing around with pendulums, that he could prove that they show that the Earth is spinning. And his first one was a huge one here. You can see it here in Paris. It was a 36-foot long pendulum. The longer the pendulum, the easier it is to observe this effect. So what he showed was this. It was this in Paris, the Pantheon in Paris, apparently. He showed that this is what happens. Okay, so we're looking here at a bird's eye view. We're looking down at the floor, and he gets his pendulum swinging in this direction at, say, 9 o'clock in the morning. Okay, so the pendulum goes back and forth like this. But at 10 o'clock in the morning, it looks like this. And 11 o'clock, it looks like this. 12 o'clock, 1 o'clock, 2 o'clock. You guys get the idea. Okay, so as time progressed, the pendulum swung in a different plane relative to the floor. And in fact, it goes through about 220 degrees in 24 hours. That's at San Francisco latitude. So what the heck is going on here? Well, as it turns out, the pendulum itself, once you get it swinging, it has inertia and it will stay in that same plane after you let go of it, but the Earth rotates underneath it, okay, or around the building. It's really kind of mind-boggling. So that's what all of these are explaining. And actually, there's a better picture of this. Oh, this one sort of shows it. I'll show you this first. So if you look here at the North Pole, if you were to get a pendulum swinging in a building at the North Pole, the floor would twist underneath it, and in 24 hours it would swing through 360 degrees. That's just bonkers, but that's exactly what would happen. Now if you changed it, though, you can see this one here on the equator. Okay, the equator, it would there'd be no change at all, because the building that you're in, or however you've set up your pendulum, would be turning with the Earth. So there'd be no change at all. So what's really cool here is looking at this animation. I'll kind of move this over here again. So here, you can see if it was at the North Pole like that, then it would look like this. Okay, this little animation, I know it's a little grainy, but you'd see, like, you would start it swinging in blue, but the path that it would map out on the ground is what's in green, and that's just cool. I mean, you could make a lot of symmetrical patterns and stuff with a swinging pendulum, and there's pendulum art and all kinds of things you could do with that, which we've played around with before. But so just worth mentioning is the fact that a swinging pendulum not only has a period and a frequency, but it can also show that the Earth is spinning. So here, actually, if you look at this, and Foucault was able to prove this, you get less and less spinning as you get closer to the equator. So a pendulum at the equator will have no change in its swinging pattern. It'll move through no degrees of arc, but at the North Pole, it would swing through 360 degrees. So that is just cool. The conclusion, though, is this, and you do not need to know how to derive this formula, but the period for a pendulum is very simple. It's equal to 2 times pi, times the square root of the length of the pendulum. So length of the pendulum goes from the pivot to like the center of mass. and you divide that by the acceleration due to gravity. Okay, so and a period, you have to remember this for questions, the period is a complete swing. So that's all the way over and all the way back. Okay, so if you have half of a period is just swinging from one side to the other. Okay, so a full period is the complete swing. So that brings us to this formula, which you're going to do some practice of. Here, let me move this out of the way. And you'll see that you need to be prepared to derive the other variables from this. So I'll just show you once here and then kind of turn you loose. And I've already posted the answers to this. So if this is your expression for the period now, not the restoring force, we already learned that. The period is 2 pi times the square root of L over G. If you need to solve for, let's solve for G first, okay? The easiest way to isolate G, because you got this square root here, is you need to square everything in the expression. So square this, and square that. If you square everything, then you'll get rid of that square root, and then you're left with t squared is equal to 2 squared is 4, pi squared is just pi squared, and that's going to be multiplied by L over G. Okay, so that's a really important first step. If you kind of do that, if you try and do it another way, you'll violate some math operations and you'll get it wrong. Okay, so from here, though, what I would do is I would multiply both sides by G and then divide by T squared. Okay, so yeah, I'm kind of just making a mess here. Let's just get back up here. So then G would equal 4 pi squared times L over T squared. Okay, so there's one derivation, which if you need to solve for gravity and all you have is a pendulum, you can do it. That's awesome. Okay, now the other one, obviously from here, is if you need to solve for L. So from this intermediate one, I guess I'll rewrite it here so it's easier to follow. From t squared is equal to 4 pi squared times L over G. From that intermediate step to just get L, I think you guys can see this easy enough. You still multiply by G and then divide by 4 pi squared. Now, the classic error that's made often when you're first learning this is that when you derive this, sure, it's going to be G times T squared, if you will, divided by 4 pi squared. The common error is you don't put 4 pi squared in brackets. Okay, if you don't do that, you'll get it wrong, because you'll go G times T squared, and then you'll divide by 4 times pi squared, and that's out of order. You need to divide by 4 pi squared as an entity, and then you get it right. Okay, so just a little tip, but I think you can manage that easy enough. So I'll let you work on these on your own because I've already posted these questions. Each of these either asks you to calculate an aspect using the period of a pendulum versus using the restoring force on a pendulum. Okay, so remember your restoring force, the masses need to be in kilograms, and for any of your period calculations, your time should be in seconds, and be prepared to use your period and frequency formulas. These guys are super useful. They're reciprocals of each other, so it's pretty easy to flip them and see if you can get these answers correct, and then check them against the key. So there's our first one.